go further with the next
So
presentation.
Nathan, you are going to share your slide, or I have your slide here?
No, you should have
I will
slides.
share my slides.
You share the slides, Nathan.
Right now, I'm not able to start the screen sharing because somebody is hiding it.
Pierre, just you stop your screen, then he able to share.
Perhaps first I can make a short introduction to Nathan.
Yes, you.
Okay, so Nathan Kölli, he studied wood science and technology at the University of Hamburg, and afterwards he started working at our university, the Technical University Ostwestfalen-Lippe. He worked in his bachelor thesis and master thesis on oil palm wood, so he has several long-term stays in Malaysia. And now he is doing his PhD on the mechanical dewatering of wet oil palm lumber, and today he will present it, what to do prior to press drying. So Nathan, we see the presentation, so it's your stage.
Okay, thank you, Katja. So welcome from my side to the presentation about mechanical dewatering of wet oil palm lumber prior to press drying. And my name is Nathan Kölli. I'm a PhD student in the Technical University of Ostwestfalen-Lippe and also in the University of Hamburg. So let's start. The structure of my presentation will be as follows. First, I will give a short introduction about oil palm biomass production, about the moisture content variation inside the oil palm trunk, about drying of oil palm lumber, and about the research approach. Then the material and methods part will come with the material procurement, the sawmill operation, and the mechanical dewatering. Then I will present the results, the dewatering rates, the extracted water, and the surface and shape. And finally, I will state the conclusions. So if we look at oil palms, they are highly productive plants. They have an oil yield of 2.8 ton per hectare and year, and at the time of plantation clearing, there are some 110 ton per hectare of dry fiber material in form of trunk and fronds. Because of this high biomass production, the oil palm has a high demand for nutrients and water. The fronds absorb carbon dioxide and produce carbohydrates like sugar and starch, and the roots absorb water and nutrients from the soil. Both is transported and stored in the trunk. The main structure elements of the trunk are vascular bundles for the transport and ground parenchyma for the storage of water and soft nutrients. Therefore, we have a high moisture and a high sugar content inside the oil palm trunk. This high moisture content is not evenly distributed inside the trunk, but there is a high variation. So in horizontal direction, the vascular bundle concentration decreases inwards in favor of the ground parenchyma. Therefore, we have a higher moisture content in the inner part of the trunk. And in vertical direction, the bottom part has a higher density and lower moisture content, and the top part has lower densities and a higher moisture content, because the material at the top is younger and softer and also is still growing. So therefore, we have a higher moisture content in the top of the palm. Then oil palm lumber is going to be used as a raw material. Drying needs to be conducted. Drying is cost intensive, what we heard before. Because of the high moisture content, a lot of water needs to be evaporated, and it is time consuming because only slow drying speed is possible. When drying speed is too high, the free water is evaporated too fast, then a vacuum develops inside the cell, and the cell walls must withstand the negative pressure. The parenchyma cell walls in the inner and higher trunk parts are very thin. They are only 2 to 8 micrometer, and therefore cell collapse develops easily, as we also heard before in the presentation before. And we see here on the picture 2 blocks of the whole diameter. The block from below is from 1 meter trunk height, and the block from above is from 3 meter trunk height, and both blocks were kiln dried very fast, and we see massive deformation and also massive shrinkage. So we are now coming to the research strategy and goal. One possibility to prevent cell collapse and to speed up drying is to remove some of the free water sap mechanically. The breast sap contains sugar that could be used for biochemicals. So the goal is to improve and to speed up drying and to extract sugars by mechanical dewatering. After the mechanical dewatering, in this research, breast drying was conducted on a single daylight press. Breast drying is fast and the oil palm wood can be densified in the same step. And the goal there is to improve the elastomechanical properties by densification. But this part of the research is not included in this presentation. The material procurement took place last year in March in a 30-year-old plantation. 20 oil palms were locked by excavator by push felling, and then the excavator loaded the trunks to a lorry which transported the trunks to a nearby factory. You see here a picture of the container, and the palms were cut in half in sections of 5.2 meters. Then 16 bottom sections and 5 top sections were loaded into a reefer container by -10 degrees Celsius and were shipped to Germany. And the sections are cut into 4 trunk parts, 1 to 4 of 2 meter length. So we see at the drawing on the right side, we see the bottom section consists of trunk part 1 and 2, and the top section consists of trunk part 3 and 4. Then the trunk parts are processed into boards in a band sawmill. The applied sawing pattern produced 4 outer boards, numbers 1, 3, 5, and 7. 4 interboards or intermediate boards, numbers 2, 4, 6, and 8. And 4 inner boards, numbers 9 to 12. The outer and inner boards are cut to 33 millimeter thickness, while the inner boards are cut to 50 millimeter thickness. There's a high density gradient in oil palm trunks, as we all know, but this gradient is much more pronounced in the outer region, and therefore outer and inner boards are cut thinner than the inner boards. The mechanical dewatering of the boards was carried out on a former glue roller machine that was modified to a roller press with a press force of 7,650 Newton on the top roller, and the feeding speed was set to 12 meters per minute. There were 3 passages through the roller press with reduction of the breast nip of approximately 20% of the initial thickness in each passage, but the compression is not distance dependent because the breast nip was not fixed. The top roller unit is elevated due to the pressure resistance of the boards when the board passes through the rollers. So then also steaming was conducted to some of the boards. 19 boards are steamed prior to thermo-mechanical compression, and 28 boards are cold compressed. So here we see a video it's in slow motion of the compression of an inner board from 3.5 to 5.5 meter trunk height. We see that there is a water wave developing on top of the board. The water is squeezed out mainly from the board's faces. Sometimes we see some small water jets that are squeezed out, and the water drains off the sides and drips into the drip pan that is positioned under the rollers. So we see that a lot of water is squeezed out. So we are now coming to the results. The mass of each board was measured before and after compression. The initial moisture content before compression and the final moisture content after compression was calculated. Then the dewatering rate was calculated as the reduction of the moisture content, which is initial moisture content minus final moisture content based on the initial moisture content. The graph shows the dewatering rate on the y-axis and the initial moisture content on the x-axis. It is differentiated between the thermo-mechanical and cold compression. The dewatering rate increases with increasing moisture content. This increase is slightly more pronounced in the thermo-mechanical compressed boards. In this graph, there's no distinction made between the board's location within the trunk diameter or within the trunk height. So we now see a graph of the moisture content reduction. The y-axis shows the moisture content and the x-axis shows the different boards' position within the trunk. We always see outer, inter, and inner boards for each trunk part. On the left side, there is trunk part number 1 from the bottom, from 1 to 3 meter trunk height. And on the right side, there is trunk part number 4 from the top part of the palm from 9 to 11 meter trunk height. And the two other trunk parts are in between. The black color columns show the thermo-mechanical compressed boards and the gray color columns show the cold compressed boards. The dashed area on top of each column shows the reduction of the initial moisture content to the final moisture content. We see that there is a wide range from the initial moisture content between the boards and also a wide range of the moisture content reduction. The outer boards and the inner boards only show a small moisture content decrease when compared to the inner boards that show a high moisture content decrease. The highest moisture content decrease is in an inner board from the top part that was thermo-mechanically compressed. On the right side, the black color column. And in this board, the moisture content was reduced from over 650% to 300%. So this slide shows the extracted water per passage. The graph shows that the share of the extracted water per passage through the roller press for the thermo-mechanical and the cold compressed boards. And in general, it can be said that half of the extracted water is squeezed out in the first passage with a slightly higher share in the cold compressed boards, because there the share of the last passage is only 19%, while the thermo-mechanical boards still have a share of 25% in the last passage. Then a multiple regression analysis was calculated with the data, and the multiple regression analysis generates an equation for the dewatering rate with an R² of 0.5. The three independent variables are x1 for steaming. If steaming was applied, then the number is 1. If not, it was calculated with 0. x2 is the position within the diameter, what is calculated or what is measured as the distance from the middle of the board to the cortex in millimeter. And x3 is the position within the height measured in meter. So the dewatering rate rises from the cortex inwards and from the bottom to the top, as we can see here. And the range is between 6 at the trunk periphery, at the bottom of the palm, and 50 at the middle of the top of the palm. So the range is between 6 and 50% of moisture content reduction of the dewatering rate. So in this slide, we see the extracted water. Also from the multiple regression analysis with the same three independent variables, x1 to x3. And again, we have an R² of 0.5. The table shows the values with the given equation for the extracted water in kilogram per cubic meter. And as the dewatering rate, the amount of extracted water rises from the periphery to the middle of the trunk and from the bottom to the top. And here we have a range of the extracted water from 42 up to 411 kilogram per cubic meter. The last slide of the results shows some examples of the impact of the roller press to the board surface and shape. Picture A shows the surface of an inner board before compression. Picture B shows the same image after compression. And small flat markers from the circumferential grooves of the rubberized rollers are visible, like small surface cracks. When press drying is applied, the markers disappear because of the further flat compression. And picture C shows a longitudinal crack at the trunk periphery. There are high densities of up to 600 kilogram per cubic meter and even more. And the density is decreasing exponential towards the middle of the trunk. Therefore, cracks can occur in this density transition zone because the different compression strength of the material. And steaming before compression reduced the appearance of cracks to some extent. Picture D shows the twisted shape of an inner board with loose edges. The parenchyma serves as a matrix for the vascular bundle system. When the parenchyma gets compressed, the vascular bundles get loose and may follow their growth direction. In oil pump trunks, the vascular bundles follow a spiral course through the oil pump trunk, and this may be the explanation for the observation of some of the boards. When breast drying is applied, the boards get even and smooth. So we are now coming to the conclusions. The dewatering rates are dependent on the position within the trunk. We have the highest dewatering rates, up to 50% in the inner and higher trunk parts. A fast compression with high feeding speed is possible with the roller press. There's a moderate effect on the surface and the shape of the boards that can be compensated partially by press drying, and steaming cryocompression softens the boards and slightly reduces the appearance of cracks and increases the dewatering rate. Mechanical dewatering with roller press is easy, cheap, and fast to reduce the high initial moisture content before drying, which is a reduction of drying time and cost. So here are the references of my paper. And thank you very much for your attention. Are there any questions?
Thank you so much.
Thank you very much, Nathan, for the presentation. To the auditorium, please type all your questions in the chat.
Yeah, if anybody have question, directly ask or type the, but I think the people have more clear with your presentations.
May I ask?
Yeah, you can ask a question. Yeah.
Yes, I wonder if at the same height of the trunk, after you dewatering, and if compared to the initial one and the one that you dewater, is there collapse change, or if they're better, or am I clear?
There is you want to know if there's the impact on kiln drying from mechanical dewatering?
On the collapse. I think the question was, if you are taking the same height and you have the mechanical dewatering and normal drying, what is the effect on collapse, was the question, if I understood the question correct.
There's a very good work from Thailand. I think you will know it on this topic. So in my research, I did some pre-tests of kiln drying of the material, and because of the compression, the surface was not even, and also the shape of the boards, they get twisted, and it was not a good result, the pre-tests. So I tried press drying, and because also one of the goal is to increase the density, and therefore I did not measure the impact on of the mechanical dewatering on the cell collapse, but some have proven that there is also a positive impact when you try mechanically dewatered oil palm lumber further on. But sorry, I cannot answer.
There's a few more questions there.
Yeah, there's the second question in the chat from Frim. The question is how much the thickness reduction was, and what about the spring back to the original dimension?
So we had an immediately spring back right behind the rollers to almost the initial thickness. So the thickness reduction varies between 20 to 50%. But afterwards, I conducted a press drying. So then I had a really higher thickness reduction, or I had a fixed thickness reduction, which was also measurable. The spring back after the rollers is immediately and almost to the original thickness.
That's
okay,
important questions. Otherwise, we will continue with the next presentation. If there are more questions, you can send Nathan an email.
Yes.
For the next presentation, I will share my screen.